Hi, good afternoon. This is our chapter 18. My name is Hope.
My name is Alyssa.
My name is Matthew.
My name is Mary Angela.
So first, the chapter 18 discusses free energy and thermodynamics. Thermodynamics predicts whether a process will occur under a given condition. So this could be either spontaneous or non-spontaneous. A non-spontaneous reaction requires energy, whereas spontaneous is a reaction that can occur without outside intervention. Spontaneity doesn't necessarily equate to it being fast or slow. For example, something in the real world that could be spontaneous is someone skiing down a slope, and non-spontaneous could be someone going up a ski slope because the hill, they're exerting their own energy, which causes them to be non-spontaneous. Thermodynamics also tells us whether a reaction is spontaneous based on properties of reactions and products. It does not tell us the pathway between the two, though, so that's something interesting. Also, we can tell a spontaneous reaction whether the H, or triangle H value enthalpy is negative. Any spontaneous process is also irreversible, so that's due to a net release of energy, but this process can only happen in one direction. And as far as the second law of thermodynamics is something that we're covering, states that the spontaneous process or the entropy is universally increased. So it's shown as like the delta triangle sign. S uni is greater than 0, and entropy is also a state of function, which is equal to the final minus the initial.
Okay, and then spontaneous processes always increase the entropy of the universe, but reactions that are like more ordered, like condensation, can still be spontaneous if they release enough heat to increase the entropy of the surroundings. So the two key factors that decide spontaneity is enthalpy, which is delta H, and that measures heat flow, and entropy, which is delta S, which measures randomness. Entropy increases when the energy becomes more dispersed, so like when gases expand or when solids melt. And entropy also depends on the possible number of arrangements, which is called microstates. So the more microstates means higher entropy, and the Boltzmann equation, which is S equals K ln W, expresses the relationship. When a substance changes temperature or its phase, you can calculate the entropy changes using changes like delta S equals negative delta H over T for the phase change, and N times Cp times ln of the second temperature over the first temperature for temperature changes. And then, like Hope said, the second law says that entropy always increases in spontaneous processes. So when the system's entropy decreases, the surroundings must compensate by increasing even more to keep the overall process spontaneous.
And then we talked about quantifying entropy change in surrounding. We said that the entropy change in the surrounding is proportional to the amount of heat gained or lost. We also have a formula for it where the temperature is constant. We also talked about entropy change in the system when we said that if a reaction produces more gas molecule than it consumes, so the delta S is greater than 0, and that if the total number of gas molecule reduced, and that the delta S is smaller than 0. We also talked about the third law of the thermodynamic. We said that the absolute entropy, which is represented by S, of a substance is the amount of energy it has due to its dispersion of energy to its particle. Then we also talked about the entropy change in the system when we said that the standard entropy of reaction is the entropy change for a reaction carried out 1 atm at 25 degrees Celsius, which is the constant temperature.
Alright, we also learned about the standard free energy of a reaction, which is a G naught, delta G naught, and the standard free energy of formation. And then we learned about equilibrium and chemical equilibrium, which is like when, like they're not changing anymore. Faster equilibrium. And then chemical equilibrium is when the rates of the forward and reverse reactions are equal and the concentrations remain constant. Then we learned about the law of mass action, which is basically like AA plus BB, and it's like, the product, same with the other side. And then the reaction coefficient, which is QC, by substituting the initial concentrations of the reactants and products into the KC equation. And finally, there was delta G under non-standard conditions, and it was delta G equals delta G naught only when the reactions and products are in their standard states, and concentration equals 1 M, and partial pressure is 1 atm. And then, equilibrium delta G equals 0, and Q equals K. That's really it.
Thank you.
Thank you.